Let's find out. Hello, science fans! Today we are going to talk about something super important in the world of electricity. It is called electric potential. Now that might sound a bit complicated, nah? But don't you worry, we will break it down. Think of it like this. Electric potential is a kind of electric pressure. It tells us how much energy a tiny charge would have if we put it in a certain spot. It is a fundamental concept really, very crucial for understanding how electricity works its magic all around us, from the smallest circuits to the massive power lines that light up our cities. It's all about energy, you see. So, what exactly is this electric potential? Imagine you have a small positive charge, a tiny little thing. Electric potential at a point in an electric field is the amount of work that needs to be done, the effort you must put in, to move this unit positive charge from a very, very far away place. A place we call infinity, for simplicity, right up to that specific point. It's like pushing a tiny cart uphill. The height you reach gives the cart potential energy. Similarly, electric potential gives us an idea of the energy stored per unit of charge at that location, all due to the electric field present there. The special unit we use to measure electric potential is called the volt. Yes, you have heard of it. When we say a battery is 9 volts, we are talking about its electric potential difference. 1 volt means that 1 joule of work is done to move 1 coulomb of charge. A coulomb is just a specific amount of charge, like a dozen is a specific amount of eggs. So, volts tell us about the energy per charge. It's a very handy unit used by electricians and scientists all over the world, making it a universal language for electrical energy. Remember that name, volt. Understanding electric potential is like understanding why water flows in a pipe. Water flows from a higher pressure point to a lower pressure point, doesn't it? Similarly, electric charges move because of a difference in electric potential. This difference is what we often call voltage. So electric potential provides the push or the drive for charges to start moving, and when charges move, we get electric current. This flow is what powers our gadgets, our lights, and practically everything electronic in our daily lives. It's the starting point for all things electric, truly. Now let's get into a little bit of the mathematics, but don't you worry, it is super simple. The basic formula to understand electric potential, which we often write as V, is V equals W divided by Q. So V equals sign WQ. Here, V stands for the electric potential, just like we discussed. W represents the work done in moving the charge. Think of W as the amount of effort or energy you spend, and Q stands for the amount of charge you are moving. It's a neat little equation that packs a lot of meaning, connecting work, charge, and potential directly. Let's try a small example to make this clearer, shall we? Suppose you do 10 joules of work, that's our W, to move a charge of 2 coulombs, that's our Q, from one point to another. To find the electric potential difference, you would just divide W by Q, so V equals sign 10 joules divided by 2 coulombs. That gives us 5 joules per coulomb, which is 5 volts. See? Simple, nah? This calculation helps us quantify the electric pressure we were talking about earlier. It gives us a number to work with, which is always very useful in science for making comparisons and predictions. An interesting thing about electric potential is that it is a scalar quantity. Now, what does that mean? A scalar quantity is something that only has magnitude or size, but no direction. Think about temperature. If you say it is 30 degrees Celsius, that's it. You don't say 30 degrees Celsius pointing north, do you? Electric potential is just like that. It tells you how much electric potential there is at a point, like 5 volts or 12 volts, but it doesn't point in any particular direction. This makes calculations often simpler than dealing with forces, which do have direction. This is quite different from, say, electric force or an electric field, which are vector quantities. Vectors have both magnitude and direction. For example, a force pushes or pulls in a specific direction, but electric potential is just a number, a value assigned to a point in space. This value helps us understand the energy landscape for charges. A higher potential simply means more potential energy per unit charge, regardless of how you got there. It's a very fundamental property of the electric field itself. Quite useful indeed for our analysis. Let's imagine we are moving a tiny test charge, a little positive fellow, around in an electric field. An electric field is the region around a charged object where another charge would feel a force. Now suppose this electric field is created by a big positive charge. If we try to bring our small positive test charge closer to this big positive charge, what happens? Well, like charges repel, they push each other away. So, we have to do work. We have to push against this repulsive force to bring our little charge closer. This work we do gets stored as electric potential energy. The closer we bring our unit positive charge to the source positive charge, the more work we have to do. This means the electric potential at points closer to the positive source charge is higher. It's like pushing a ball up a hill. The higher you push it, the more potential energy it gains. So, moving towards a positive charge, with a positive test charge, means you are moving to a region of higher electric potential. The electric field is trying to push your test charge away, but you are overcoming that push, thereby increasing its potential energy. This is a key interaction. Now let's flip the scenario. What if the electric field is created by a big negative charge? And we again have our small positive test charge. Positive and negative charges attract each other, they like to come together. So if we place our positive test charge near the negative source charge, the electric field itself will pull the test charge closer. The field does the work this time, not us. As the positive charge moves closer to the negative charge, it actually gains kinetic energy, it speeds up, because the field is doing work on it. In this case, as our positive test charge moves closer to the negative source charge due to the attractive force, its electric potential energy decreases. This means the electric potential at points closer to a negative source charge is lower, or more negative. It's like a ball rolling down a hill. It loses potential energy and gains speed. So, when a positive charge moves towards a negative charge, it is moving from a region of higher potential towards a region of lower, or more negative, potential. The system naturally wants to move to a lower energy state. Understanding electric potential is all about understanding energy in electrical systems. When you move a charge against the direction an electric field wants to push it, you are putting energy into the system. For example, if you have two positive charges, they naturally want to repel each other. If you force them closer together, you are doing work against this repulsion. This work is stored as electric potential energy. The electric potential at their new, closer positions will be higher, reflecting this stored energy that you have added. It's like compressing a spring. You store energy in it. Conversely, if you allow charges to move in the direction the electric field naturally pushes them, the system releases energy. Consider a positive charge placed near a negative charge. They attract. If you let the positive charge move towards the negative charge, the electric field does work on the charge. The charge speeds up, gaining kinetic energy, while its electric potential energy decreases. This is the system moving to a lower energy state, which is something that happens spontaneously in nature. It's like letting a compressed spring expand. It releases its stored energy. This concept of energy difference is why electric potential, or more accurately, potential difference, voltage, is so incredibly important. A potential difference between 2 points is what makes charges flow from one point to the other, creating an electric current. Think of a battery. A battery maintains a potential difference between its positive and negative terminals. When you connect a wire or a light bulb between these terminals, charges flow from the higher potential point to the lower potential point, releasing energy that can light up the bulb or power your device. No potential difference, no current. So, grasping electric potential helps us understand how energy is stored and transferred in electrical interactions. It's fundamental to designing circuits, understanding how batteries work, and even how our own nerve cells transmit signals using electrical impulses. It's not just an abstract idea, it has real-world applications all around us. Knowing about electric potential unlocks a deeper understanding of the invisible force that powers so much of our modern world. It's all about energy and how charges interact with each other due to their electric fields. Pretty neat, huh? Science is cool.